Welcome to Introduction to FlightStream. We will show you how to import a CAD model, apply mesh to it, and how to run it in a flow simulation for a flight condition. Right here, you are looking at the FlightStream user interface. The application menu provides access to simulation files and other functions which will be covered in other videos. The Simulation tab gives access to the simulation tree or sim tree. You can control your CAD model, mesh and simulation type settings. The Property tab shows you mesh statistics, mesh controls and solver parameters. The Output log window is where FlightStream text messages and information are shown. That includes all solver convergence data, process and error messages. The Scene window shows the current geometry, mesh or solver results. Finally, there is the toolbar for viewing, selection, solver and manual geometry repair options. We will start with a Piper PA-24 CAD model. This way you would only need to fix any CAD issue on the half side and then mirror the model after the fixes are done. This will save you time from trying to fix the entire CAD model. Let's import a CAD half model into FlightStream. Right-click on the CAD node in the sim tree and choose Import. FlightStream currently support all ISO standard IGES entity type. Select an IGES file to open. We will keep to the default IGES import settings for this demo. The more complex your model is, the more time FlightStream needs to import the model. Great! We see the model has successfully imported. Keep in mind that this is not a FlightStream best practice, but an introductory demo. Let's proceed to split the model surfaces into different body parts so that it will be easier to work with the mesh setup. Here you see there's a body 1 and floating faces. Sometimes during CAD creation and IGES import, some floating faces at the origin will show up. We will use split body action to group the body parts we want to use. Press F1 on your keyboard to switch to top view. From the toolbar, click on the toggle global mesh wireframe view to turn off or on the mesh on the model so that you can get a better view of it. Our first body split will be the wing. Activate Select Faces tool from the toolbar. Deactivate other select patches, faces, edges or vertices if activated. Using the Selection Lasso tool, click to drag a box around the wing geometry. Double-click to close the selection and the wing is now selected. Right-click with your mouse and choose Split into New Body option. You notice a new entry named Body 3 is created under the CAD node in the sim tree. Let's rename the Body 3 to Wing. To do so, with Body 3 already selected, click on Body 3 one more time, wait for a second and type Wing to replace the Body 3 name. Next, right-click on the newly renamed wing body part and choose Set Color. We will set the wing to blue color so that we can spot it easily. Repeat the steps to split the horizontal tail, vertical tail, and fuselage from each other. With each body part split action, a different color is assigned for easy visual identification. After the body splits are done, we should check on the topology for the CAD surface diagnostics. Click on the Topology tab and you will see a table of different diagnostics available. Click on the Refresh button to start the diagnostics. Some numbers will populate and generally you should pay attention to those numbers that are in the red boxes. If we have degenerate faces, double-click on the red box to select these faces. To remove them, on the toolbar, click on Deleted Selected Faces tool. Click on the Refresh button again to confirm that the degenerate faces are gone. With these faces deleted from the mesh model, check that the removal did not leave any unintended holes. If holes are created, the count in free edges will increase. We will show you how to fill up holes in another video. For our case, we do not have any numbers in the red boxes. But we do have 27 free edges in the green box. Free edges are edges of mesh triangles that have no neighboring triangles across the edge. To see where these green free edges are, we will zoom in closer to the nose of the airplane. Here you can see the spinner and the fuselage have free edges, which means there's probably tiny gaps between these two surfaces. To view the tiny gaps, we will need to zoom in quite a lot. To help with such a close zoom in action, we need to set a vertex as the axis origin near where we want to zoom in. Deactivate the Select Faces and activate the Select Vertices tool. Click at a corner point close to the green edge and then click on Make Vertex into Origin tool. A XYZ coordinate now appears at the corner point where you have selected. Use your mouse scroll wheel and scroll up to zoom in close enough to see the tiny gaps. Now that we have visually confirmed the tiny gaps are there, we need to seal them up. To select the green edges, we need to deactivate the Select Vertices and activate the Select Edges tool. Place the mouse cursor slightly to the left of the left green edge and click on your mouse button. This selects the edge as it turns from green to magenta. You can also confirm that from the selected curves counter in the scene window. Next, we want to select the edge on the other side of the gap. Move your cursor to the right of the right green edge and click on the mouse button to select the edge. With both edges selected, as confirmed by the selected curves counter at 2, right-click on your mouse and choose Mark Curve as neighbors. This action tells FlightStream that these two edges are actually one common edge and no gap should exist there. To make that happen, we need to retessellate the mesh. Toggle the mesh display on so that we can see the current mesh. For this demo, we will apply the retessellation to the entire airplane. Under the CAD node, select the wing body part and hold down the Shift key. While keeping the Shift down, click on Horizontal Tail, Vertical Tail and Fuselage to select them. Move your mouse cursor to the scene window and right-click in the empty space. Choose Retessellate, followed by Trimmed Mesher. Trimmed Mesher can be used for non-lifting surfaces and Aligned Mesher would be more suitable for lifting surfaces like wing and tail. Trimmed Mesher is used here just to get some quick results for demo purposes. More details on how to use Aligned Mesher will be shown in other videos. We will change the tessellation edge size that is a little on the larger side. If the tessellation edge size is too big of a value, you lose the general shape of your CAD model. On the other hand, a tessellation edge size value that is too small will unnecessarily prolong the meshing and running of simulation time without any benefits of getting more accurate results. For this demo, we will go with a value of 0.12. It will take some time to mesh. Now we can zoom in and take a look to see if the gap is gone. As you can see, there is no more gap and the vertices between the two surfaces now meet up nicely. The CAD model is now ready to convert to mesh. We only need the four body parts, namely wing, horizontal tail, vertical tail and fuselage. We can ignore the floating faces body part. With wing, horizontal tail, vertical tail and fuselage body part selected, hold down the Shift key and right-click on wing body part to choose Convert to Mesh option. You can let go of the Shift key now. Expand the mesh node in the sim tree and you will see the same selected body parts listed there. You can see the axis origin is still set near the spinner. We should reset that to the actual origin so that it would not mess up our simulation later. Right-click in the scene window and choose Reset the Reference Origin option. Before we initialize the FlightStream solver, there are two important things to define if we have any trailing edges and wake termination nodes. What are trailing edges? In FlightStream, these are edges marked to indicate where the vorticity is shed off lifting surfaces that will start the shed vortex wake downstream. In this example, we will need to mark the wing and horizontal tail trailing edges. Right-click on the Trailing Edges node and choose Detect by Surface. Since we defined the body parts in our CAD and mesh, we get to select which surface we want to apply the trailing edges. Check the boxes for wing and horizontal tail and then click Done. We can rotate the view to see that there are red lines on the wing and horizontal tail. Zooming in closer, we see some edges at the wing tip are also marked as trailing edges. That is not what we intended, and to remove them, we can use the selection lasso tool. Activate that and drag a box to surround the red edges at the wing tip. From the selection, extra edges are selected, but we don't need to worry about that. Right-click on the scene window and choose Delete Physics from selected elements. Since the extra edges do not have any physics associated with them to begin with, there is no harm done in deleting the physics from these elements. Now let's set the wake termination nodes. These nodes are points to tell FlightStream to terminate any wake strand where there should not be any vortex shedding. A good example would be the point where the wing trailing edge meets the fuselage. Right-click on the wake termination nodes node and choose Detect by Surface. Same as before, we get to select which surface we want to apply the wake termination node. Check the box for wing and then click Done. You can see a red dot is added to the wing trailing edge where it meets the fuselage. Before we move on, there is a minor mesh issue near where the vertical tail meets the horizontal tail. Let's zoom in to see what issue we are looking at. Whoa! We lost our mesh there for a while. Remember earlier we used the trick to set up a vertex as the reference origin? We need to do that here so that we can zoom in very close to where the mesh issue is. Let's activate the Select Vertices tool and deactivate the Select Edges tool. We see that there is a tiny gap between the vertical and horizontal tail. Double-click in the scene window to resize the coordinate axis when it is obstructing your view. One quick tip here is that we can merge the vertices and close the gap at the same time. To do that, we first select the vertex we want to keep. Then activate the Selection Lasso tool, drag a box around the vertices we want to move and unite. With the vertices selected, click on the Merge Vertices tool and now the vertices are moved to the first vertex location. The gap is now closed too. Let's not forget to reset the reference origin. Now we are all set with the mesh. Another good thing to check is that the units are set correctly for your simulation. In the Property tab area, click on Controls tab and you will see the simulation length units is currently set to feet. That means when we look at the solver runtime parameters, the FlightStream velocity, reference length and area would be in feet or feet squared. One key thing to remember is that the reference area entered here should be reflective of the model setup you choose. If you want to simulate a full airplane model, you should put in the full wing reference area. If you decide to simulate half of the airplane down the symmetry plane, then you should enter half of the full wing area. Note that we have set the number of parallel processors to 8. Keep in mind that FlightStream is fully parallel enabled, so this setting should match the maximum number of available processors to run simulations efficiently. With everything set, we can click on the Initialize Solver button on the toolbar to tell FlightStream what we want in the simulation. For this example, we want to activate the mirror along the XZ plane since we want to simulate a full airplane. For the wake strand termination, we will go with the value by clicking the default button. We will leave other settings unchanged and click on Initialize button. From here, it will take a short while in FlightStream to build the model and get it ready for the simulation run. Let's speed up the process and you can see it takes about 33 seconds in real time to initialize this model. As you can see, we now have a full airplane ready to run in a simulation. You can toggle the mesh off to gain a little time saving. Alright, let's click on the Run Solver button to get the simulation started. The simulation looks to be running smoothly. Let's activate the wake strand and see how that looks. From the scene window, click on the gear and wrench icon, which is the scene settings button. This brings up scene display controls on geometry, solver, wake and post-processing. To activate the wake strand, click on the Wake tab and check the box for strands. Now we see these lines representing the wake behind the airplane, but notice the lines are all straight. FlightStream will show the rotating vortex once the simulation comes to a stop. Beside coefficient of pressure, you can also select different contour parameters. Right-click in the scene window and you can change the displayed contour parameter to any of the available options at any time during or after the solver run. The options include vorticity, Mach number, coefficient of pressure, static pressure ratio, various boundary layer parameters, and etc. With the convergence threshold set to 1e-4, FlightStream Solver Convergence checks the surface velocity and surface pressure residuals at each iteration. The simulation run will stop once both residuals drop below the convergence threshold, which happens to be 1e-4 for this demo. We will continue to let the simulation run fast forward till it stops after the convergence threshold is satisfied or the run reaches the set iteration of 500 for this demo. After 2.5 minutes, the simulation is done. The wake strands are updated and you can see the vortex formed at the wing tips. To look at forces and moments of this simulation run, click on the Analysis tab. See that exclamation mark in the Refresh Solver Data button? That means we should click on that to get our forces and moments results. Once updated, you see the final values for lift coefficient CL, induced drag coefficient CDI, skin friction drag coefficient CDO, and other moment coefficients. If you do a quick search on the internet for a NASA report TND 5700 for full-scale wind tunnel investigation of a light single-engine airplane, you can find lift and drag data of this Piper PA-24 airplane. Taking a quick peek at the NASA report, the lift coefficient for this airplane at zero angle of attack is around 0.26 and FlightStream shows 0.29. This is great for an analysis done under 3 minutes. How about the drag coefficient? The NASA report shows a CD of 0.0299 and FlightStream has 0.0191. With further mesh refinement, FlightStream results would improve. We will talk about meshing in details in another video. Other than the airplane surface pressure or vorticity results, we can switch to plots in the scene window. The residual plots for velocity and pressure show a nice convergence to below 1e-4 set threshold. We can also see the convergence for lift coefficient, induced drag coefficient and pitching moment coefficient by right-clicking in the scene window and choose Plot Lift, Drag and Moments versus Iterations option. To see the lift distribution across the lifting surfaces such as wing and horizontal tail, we can right-click in the scene window and choose Plot Sectional Forces. From the Sectional Plot Options window, change the X-axis option from X to Y so that we are looking at the span-wise direction for the results. The plot here looks like a smiley face, but this is actually the wing and horizontal tail 3D lift distribution. The legend in the top left corner of the plot tells us that the black boxes represent the wing data and the red triangles represent the horizontal tail data. As expected, the wing produces most if not all of the lift and the tail provides negative lift counterbalance so that the airplane is in equilibrium. This concludes this FlightStream introductory demo video. If you would like to see more FlightStream videos, check out these other ones from our channel. Smash the thumbs up like button, or hit the subscribe button to get notification of new videos. Thank you for watching.